Thank you very much. I really appreciate the invitation to this meeting, and I'm really sorry I couldn't make it there in person. Anyway, the organizers asked me to talk about some of the recent developments of sensing using nitrogen vacancy centers in diamond. And here's a picture showing our hero. And my title here is a bit of a play on words: sensing and envy, right? That should resemble ideally the title of a cheap novel. But anyway, let us get going. So probably you heard a lot about envy centers by now, but if there are some newcomers to this field, I'll say a few words in the beginning. So on the left here, you see a jewel. It's a diamond that we cherish for its beauty. And on the right, you see a similar size artificial single crystal and very pure diamond that is basically almost free from any kind of defects. And what you immediately notice is that this is beautiful and this is very boring. It just looks like transparent piece of glass or something, only with high refractive index. And so it turns out that the beauty is actually not in perfection, but the beauty is in the defects. And some of these color-centered defects is what we enjoy in diamond. And there are thousands and thousands of them. They're very different. But the one that is particularly interesting for us is the nitrogen vacancy center. And you can think about this as here is the lattice of carbons in diamond, and you take two adjacent carbon atoms and you remove them from the lattice, and then you replace one of the so you put into one of the vacancies here a nitrogen atom, substitutional nitrogen, and you leave the other vacancy just that, a vacancy. And here you go, you have this nitrogen vacancy center that has amazing properties. But it turns out that it's not that simple. You have to sometimes work to prepare a diamond containing the right concentration, the right type of color centers. And so the procedures are quite different. So if we want to have a high density diamond, we usually start with a material which is called type 1B diamond that already has a lot of substitutional nitrogen, and that gives this yellowish color to it. And it doesn't have so many nitrogen vacancy, so not so many vacancies even to start with. And so to make the vacancies, what we do, sorry about that. It's to make the vacancies, we irradiate these crystals with high energy electron beams. We use high energy beams so they go through the material and don't get stuck there. And as they go, due to ionization losses, they create vacancies on their way. And now we have vacancies and nitrogens, but they are not yet united into the nitrogen vacancy centers. So to do that, we anneal the diamond at the temperature of 700-800 degrees, maybe 1,000 degrees Celsius for a few hours. And this makes these vacancy mobile. They drift around in the crystal. They find their nitrogens, and then they unite in these nitrogen vacancy centers. And then high density sample looks like this. It's kind of purple. So that's one way. Now there are many other ways to prepare the diamond, but that's to give you an idea about one procedure. Now, what do you do with it? Well, you can see this is a vintage picture taken, I think, in 2008. So the style of the laser pointer shown here is kind of old. And this picture already is taken with a cell phone. What you do is you take one of these crystals that are typically 3 by 3 by 0.5 millimeter, and you shine your green light, and you look at it and you see that it fluoresces in this kind of red color. And you might ask, how come I excite with the green and it fluoresces in red? You can actually put this sophisticated experiment that you are seeing onto scientific basis and collect this fluorescent light and send it on a spectrometer if you like. And then the excitation here is 532 nanometer. You don't see it, it's over here. And then the spectrum of emission looks like this. There is a sharp line at 638 nanometers, and then there is like a broader feature on the longer wavelength side. And if you look closely, there's actually two families of this kind of similar structure, and it turns out that this family belongs to the neutral nitrogen vacancy centers. And if a nitrogen vacancy center gets an extra electron, usually coming from a nitrogen donor, then it becomes negatively charged, and this negatively charged center, it turns out to have the amazing properties that we use for sensing. So this sharp feature is called the zero phonon line, and that's when you have an electronic excitation that doesn't involve also vibrational excitation. If there is vibrational excitation, this gives rise to this so-called phonon sideband. And there is this phenomenon that we are observing here. It's called the Stokes shift. That the absorption is at shorter wavelengths, higher energies than emission. And you can see this here. So this is the ground electronic state here, and this is the vibronic excitation band, and the same thing is happening in the excited state. So when we are looking at absorption, we usually have electronic excitation accompanied by some vibrational excitation. Then we have non-radiative decay on a picosecond time scale over here to the bottom of the band. And then there is normal emission after about 10 or so nanoseconds back to the ground state. And again, we can excite vibrations when we do this. And so you can see that, this leads to the shift. Now, this is a picture. This is your nitrogen, this is the vacancy, and these are the three adjacent carbons. And it turns out that this picture containing, if you like, 5 elements is the simplest cartoon representation of the center, and it gives you the idea of the molecular symmetry of this. And so the labels that you see here are actually the labels of the symmetry group corresponding to this kind of structure. And so one of the amazing things is that the center has a triplet ground state, so it means that there is spin 1. Due to this this kind of symmetry, it's not exactly isotropic space here. So this symmetry allows you the ms equal to 0, the 0 projection on the NV axis to be split out of plus minus 1 projections, but these ones are sensitive to the magnetic field. Well, the whole thing is sensitive to the magnetic field, but if you apply the magnetic field along this axis, then nothing happens to ms equal to 0, and plus minus 1 linearly shift in magnetic field that enables eventually magnetic sensing. The other important thing that you see here is that there are also singlet levels that are located somewhere between the ground and the first excited triplet state. And it turns out that this kind of a structure, it enables a convenient optical polarization. So what you do is you just shine, let's say, green light, and you do nothing. You don't worry about any polarizations or anything. And you find that your NV centers assemble, say 90% of them assemble at the ms equal to 0 state. So it's easy to optically initialize the state. And because this intersystem crossing shown here depends on the spin projection, So it's a spin-dependent process. It can also be used to probe what kind of spin state your center is in. And it turns out that if you're in ms equal to 0 state and you go here, then the most probable event next is that you're going to fall down here, and this leads to bright fluorescence. And if you are in one of these plus minus 1 states, then you have a higher probability to hide for a while in these singlets, and there is less fluorescence. So almost for free, we get a possibility of initialization and optical probing of the NV center. And if you look at this picture, this kind of look like atomic levels. And indeed, you can play some games that are very similar to what we do in atoms. For example, you can, under certain conditions, have electromagnetically induced transparency, just as an example. But it is a bit misleading to think about this as an atomic system or even a molecular system, because after all, this is a solid state system and has all kinds of solid state peculiarities in it, and one of them being the sample dependence. The properties of the center really could depend somewhat on which kind of diamond it is in, and even on the individual center. So here is the diagram in a bit more detail with transitions shown, and that, in fact, the singlets that I showed as one level are also a pair of levels, and sometimes we use this transition between the singlet levels as one of the ways to diagnose the center. But now that I kind of gave you a bit of a glimpse about the system, let me go back to this highly sophisticated experiment, as I already said, and show how to further convert this into a magnetometer. So what you need to do is you need to take a magnet and you need to wave it around this system. And if you wave a magnet around here, you notice by eye that the brightness of this emission changes. So there is a dependence of the luminescence on the magnetic field. And so great, my signal depends now on the magnetic field. I have a magnetometer. So once again, we put it on a scientific basis. We align our magnetic field to be along one of the axes of the crystal, and then we record the fluorescent signal as a function of magnetic field, and we see this beautiful picture that shows that there is some dependence at relatively small magnetic fields, and then there are all kinds of sharp features. And it turns out that all of these features, no, I said something wrong. Most of these features are well understood. Some of of them are still not quite identified. For example, this overall decay of fluorescence at low field, it has to do with the NV centers that are not parallel to the magnetic field, but at an angle, and there occurs magnetic, you see this is nonlinear Zeeman shift, and mixing between sublevels that reduces the fluorescence contrast, and that's why you see this overall decline. And then there are crossings of the levels at certain magnetic fields that also leads to this so-called cross-relaxation features. And then apart from the NV centers, you have other things like the substitutional nitrogen atoms that are not paired with NVs. These are called P1 centers, and they also have non-zero spins, spin 1/2, and there is also nuclear spin involved. And in the end, you have all kinds of crossing here. And I would like to draw your attention to this one in particular. This is a so-called ground state level anti-crossing, or G-slack, and this is when this m equal to -1 sublevel for the NV centers that are parallel to one of the axes, or to the axis parallel to which the magnetic field is applied. It crosses or nearly crosses the m equal to 0 sublevel, and then there is a strong and sharp feature. And so using these features, we can actually make a magnetometer that sometimes doesn't even require any application of any kind of microwave fields. So these are called microwave-free magnetometers. But this gives you, again, an idea. So now I guess I would like to finish the introductory part of my talk and give you just a few examples of what has been happening recently. And it's hard to sort of make a full catalog, so I decided to just stick with the work that our group is involved in. So microwave-free vector magnetometers. Vector magnetometer is a device that not only measures the magnitude, but also the direction of the magnetic field. Then a technique for wide field imaging that combines magneto-optical Kerr effect and V-magnetometry. This, I'm going to show you a lot of pictures of this. There's also zero field magnetometry that eventually we will hope will allow us to realize something that I call extreme NMR. This is one spin NMR or a single molecule measured with a single spin sensor and everything happening at zero magnetic field. So that is what extreme NMR is. And finally, I'd like to show you some pictures of rotation sensor based on NV centers that have been just realized this year, even though these things have been proposed quite a while ago, 2012 or so. So one of the projects that we have is called PROTOS, probing topological spin structures using concurrent complementary modalities. This is motivated by recent work of condensed matter colleagues, in particular Professor Chloe here, who have studied these very interesting spin structures on the surface of solids, and we decided to kind of look into this together with them, with this set of wonderful collaborators. And the motivation for this is that magneto-optical Kerr effect, which is just a change of the polarization of light that is reflected from a magnetized surface, combined with measuring magnetic field using NV centers. But you might say, aren't these things related? Isn't the magnetic field produced by magnetization? So wouldn't be the same? And I would like to argue to you that it's not always the case. So you're all familiar with little sheets, magnetic sheets that you stick to the refrigerator. And I invite you, if you haven't done this yet, I invite you to take two of such magnets and then try to slide them one with respect to the other, the refrigerator side towards the refrigerator side. So try to do this. And what you will find is maybe to your surprise, maybe not, that these things are actually something that's called Halbach array. This is actually a periodically poled magnetized structure. The period is maybe a millimeter or so, and it's up, down, up, down, up, down. And this is done so the magnetic field actually escapes the magnetized sheet. If you have a uniformly magnetized sheet, doesn't matter in which direction, there will be essentially zero field outside, only very tiny fringing field at the perimeter here. But this is a beautiful result, that uniformly magnetized sheet doesn't have a field outside. And so this immediately explains this. So if you are studying for some reason the uniformly magnetized sheets, then you will measure no magnetic field, but you would measure a big Mach signal because the magnetization is still there. And this way, you can say a lot about the structure that produces the magnetization. So our colleagues in the condensed matter department, they gave us some interesting surface magnetic domains, and we built an apparatus. This is magneto-optical Kerr effect apparatus, and we have looked through this and recorded the structures. They look like worms, so to say, and you change the magnetic field, these worms, so move around, and as you can see, and unite, and so on. So this is a 40 by 40 micrometers field of view over here. And we do this in apparatus in which we can very easily just flip one mirror and sort of change from the measurement of this magneto-optical Kerr effect to imaging with nitrogen vacancy centers. And so we can look at the same structure with these two modalities. This was published in Physical Review Applied just recently this year. And then we can build these pictures and superimpose them together and see where they resemble each other and where there are differences. So it's a nice new tool for studying surface magnetism. And this is just the beginning. There are lots of ways how this kind of device can be improved. And so we're kind of excited about it. Let me now show you a few slides about how we measure or try to measure, I guess we do measure zero magnetic fields. So if you, the standard technique I should mention of measuring magnetic field is something that's called optically detected magnetic resonance. And the idea is that you initiate your nitrogen vacancy centers in the m equal to 0 sublevel, as I explained before. And then you apply a microwave field and you drive a transition to one of the m plus minus 1 states. And that tells you what the frequency is. Now, I didn't really go in great detail about the hyperfine structure. So there are nitrogen, nitrogen 14, the most abundant isotope of nitrogen. It has, it has nuclear spin 1. And so you see that each line or family of lines, it splits into 3 components, and it's not a problem usually. But if you look in the region of 0 field, you see that the lines are always coming together, and as a result, if you want to measure really near 0, you have only quadratic dependence on the magnetic field and rather than linear, and so you basically lose all your sensitivity there. And not to mention that there are other effects in crystals. There is, for example, a strain effect that mixes the magnetic sublevels, and it has been for many years sort of the notion that you cannot measure 0 fields with nitrogen vacancy centers. But this is not exactly the case. And in fact, you can set up a system where your microwaves are, instead of being linearly polarized, as usually the case, they are rotating microwaves, circularly polarized. And in fact, it was Professor Gawlik from Krakow, whom you may know, who is a longtime colleague and collaborator, and he taught us a little trick about how to do this. And it involves having a magnetic field produced by 2 parallel wires that are phased in a particular way, and changing this phase in a particular line above these wires will be here. You can create either left or right rotating circular field. And with this, what you can do, so this is the picture made with linearly polarized microwaves, and these are circularly polarized microwaves. And you can see that you can basically kill one of these families and now have resonances that actually are linearly dependent on your magnetic field in the zero field. And in this work, we have demonstrated, in fact, a zero field ensemble magnetometer. Now, why would you want to do this? Why were you interested in the magnetic fields? Well, there are many reasons. Our own motivation comes from doing this particular kind of nuclear magnetic resonance measurements that are called zero to ultra low field NMR measurements. But other people may be interested in this as well. For instance, a lot of magnetometry for biomagnetic fields, for instance, brain magnetometry, is done in shielded rooms, and there the field is also near zero. So this could be very useful. So what I've told you so far pertains to ensemble magnetometry, but sometimes you want to work with just one nitrogen vacancy centers. And long story short, this method that I described also works very nicely for single NV centers as well. And this has been recently published in Quantum Science and Technology. So with these single spin zero field measurements, we would like to, in fact, do this extreme NMR. Here are pictures of actually individual NV centers, and we check that these are individual centers doing measuring the second order correlation function of emission or Henry-Brown-Twiss type experiment. And so we are working with colleagues from Ulm, Professor Zhilesco, for instance, on achieving the zero field nuclear magnetic resonance measurements. So this picture shows some single spin NMR lines, unfortunately not yet at zero field, but we are moving quickly in that direction. So the zero field NMR idea is maybe a bit unusual, because if you say, oh, I'm doing NMR, people usually think big magnets as strong as possible. And this is not stupid. There's a reason for it, because there are 3 stages of an NMR experiment. You need to polarize the spins, you need to encode the information that you are after, and then you need to detect the spins. And normally you need strong magnetic fields for all 3 of these stages. But we are doing the kind of NMR where we invent or utilize techniques that don't rely on magnetic field for each of the stages here. And this is similar, if you like quantum computers. These 3 stages are similar to initialization, operation, and readout, basically the same thing. So how do we get rid of magnetic fields? For instance, to polarize the nuclei, we rely on things like dynamic nuclear polarization, laser optical pumping, or this beautiful technique called parahydrogen-induced polarization. But my favorite actually method is what I call do nothing method. So just do absolutely nothing and your sample is polarized. How can this be? Well, imagine that there are n spins and you randomly sort of make them up and down randomly, each one. So if you have n of these, you will get an excess of spins polarized in one particular direction over the opposite one of about square root of n, because it's just statistics. And now imagine that you're going to smaller and smaller numbers of spins, and eventually square root of 1 is equal to 1. So when you have one spin, it's what's called stochastic polarization. Signal is just as big as full polarization that you get with any other method. Then in encoding, for instance, if we do NMR spectroscopy, we do not rely on chemical shifts that would need big fields, but we rely on something that's called J coupling. And that is in atomic physics language, second order hyperfine coupling, and that also doesn't rely on strong fields. And I should say that you can use diamond these days for each of the 3 stages here. For instance, for detection, here is an example of a recent experiment done in the group of Professor Victor Acosta at University of New Mexico, where a small quantity liquid NMR is detected with specially profiled diamond sensors here. You can actually polarize nuclear spins in diamond and then try to transfer the polarization to the sample. You want to measure, a lot of people are working on this, and also you can use these diamonds for encoding somehow.
Dmitry, 10 minutes.
Oh, perfect. Thank you. So I want to say that the zero field nuclear magnetic resonance used to be a bit of a fringe in NMR, but it is changing now. And a few years ago, we were able to convince the Marie Curie organization to finance an innovation training network, which has now trained about a dozen of PhD students in this field in Europe. And the lead organization for this ITN is actually Krakow. Professor Szymon Pustelny is our leader there. And there was a meeting at Mainz, and some of the students in this network are seen here. So finally, I have just a few minutes, so I'd like to tell you just a few words about measuring rotations with diamond. We had this idea some years ago, 2012, and it turned out that our colleagues at MIT also had a similar idea, so they published right after us. There was closely related work done also by colleagues in Australia. So there were 3 papers about diamond and rotations, and 2 papers explicitly proposed rotation sensing based on diamond. But I must say that the first actual realizations of rotation sensor had to wait until this year. But now it's realized. And so there are 2 kinds of sensing that you can think of. So if you are rotating around the symmetry axis of the NV center, you can measure just a dynamic phase, so to say. But if you then take the diamond and you rotate the whole thing around an axis that's not collinear with the axis of the NV, then under certain condition, you can acquire Barry's phase or geometric phase, and you can also use that to determine rotations. And here it is important not to be sensitive to magnetic noise and to be sensitive to rotations. And so the systems of choice are then nuclear spins rather than electronic spins. And it's nitrogen 14, nitrogen 15, this is a spin 1/2 nucleus, or C13, which is also a spin 1/2 nucleus. So far, up to now, this N14 sensor has been realized. So the sensitivity is given by this equation. And what you see here is that there are really 2 main parameters: is how many centers you can interrogate at one time, and what is the spin coherence time. There's not too much. Here's the measurement time, and then there's contrast and so on. But the main parameters, like I said, is the number of spins and coherence time. And if you put in the numbers, you get some kind of performance that is not spectacular. Actually, it's very far from the record results obtained with things like fogs. This is fiber optics gyroscope, with many kilometers of fibers wound, or maybe what is it called, the atom interferometer gyros. But this is not really a competition to these devices. It could be a competition to some tiny devices that are smaller than even the MEMS. Anyway, I'm running out of time. So there was a lot of preliminary work done in that direction, spearheaded by Andrei Yermola. So the first thing to do was to develop efficient mechanism for polarizing, in this case, the nuclear spin and reading it out. I'll skip the details here, but just gonna say that it was possible to devise a microwave free technique of direct interrogation of nuclear spins, and that worked very well. Now we have optically detected nuclear magnetic resonance, or the NMR, if you like. Then this allowed already measurement of temperature dependence of the say quadrupole splitting in the between the nuclear levels, which confirmed what we were suspecting, that there will be significantly less sensitivity to environmental perturbation for these kind of transitions.
Dmitry, we have 4 minutes, last 4 minutes for questions.
Yeah, okay. So we should stop. I just want to say maybe that this is the picture and this is the rotating platform, and it works, and you can dial how fast the platform is rotating and then read it out with the sensor. And then you can even, if you want to have some fun, you can even write NV with the rotation sensor and then read it out. Or even, this is less impressive, but maybe if you look here, you can read NMR, okay? All right, so this is working as well as we expect, and we still have a lot of room for improvement. And I'm not going to tell you how we're going to improve it, but here is my summary slide. Sorry for going a bit over time. I got carried away. So to say, so I told you about the combined MOG and NV sensing, about zero field magnetometry towards extreme NMR, and then I guess I gave you some teaser images of actual operation of NV-based rotation sensor. Thank you so much for your attention, and I hope there's still time for a question or two.
Thank you. Okay, questions? Okay, one question from Jean Delibert. The first one is, okay, Michał Karpiński, the first one. Can you?
No, this is the session. So Jean Delibert.
Sorry. Jean, can you ask your question?
Sure, I can do it. Thank you for the nice talk. I'm asking about the gyroscope application. I'm wondering which one of the two phases you mentioned is dominating between the dynamical and the geometrical one. I mean, should we think of this like a Foucault pendulum, or is it just the dynamical phase which is dominating?
Yeah, so far the device that we have realized, we deliberately tried to just use the dynamic phase, so to rotate it around the symmetry axis. We think that the effects due to the Barry's phase should be just as big, but this is one of the next steps. So we have worked this out theoretically in the 2012 paper, but we haven't seen the Barry's phase. But this is like really, we think that we don't even need too many changes in the apparatus. So this is one of the next steps.
Okay, that would be neat.
To see what, yeah, it would be very neat. Yes.
Yes.
Any further question? Yes, Michał.
Hello. So why would I want to use your rotation, your gyroscope instead of an optical gyroscope, and how does the sensitivity compare?
The sensitivity is miserable compared to that. Okay, so the competition. Yeah, so the competition will never be these big things that weigh hundreds of kilograms and so on. So the possible competition would be MEMS or something that even smaller than MEMS, and with all the solid state advantages, for instance, the wide range of operation conditions, bandwidths, and things like this. But this is basic demonstration of the basic sort of functionality at this point. It's a bit, of course, we have things in mind, but it's a bit early to talk about this as a competitive device. But we're actually very happy that we were able to see the predicted effects. So maybe it's more of basic science at this point, but we'll see where it takes us.
I suppose miniaturization is indeed.
Of course, this is in principle, this could be tiny. Yeah.
Thank you.
Okay, and a quick question. Otherwise, you have to move on. So thank you again, Dmitry.
Thank you.